Okay, good afternoon, everybody. So, I will be talking something new uh, in this session, which has not been talked about much in previous sessions. Is I will talk about mostly about astrophysics. Okay, and the title of my talk is the strange case of twin neutron star. So, what do we mean by twin neutron and star? We will be going through that. So, before I start my talk, just thanking you all for inviting me, and let us start what do we know about and what the things that I am talking about. So, first I will talk about neutron stars. Neutron stars were first theorized by Bade and Zwicky just after the discovery of neutrons. However, their observational counterpart, were the pulsars, were discovered much later. Okay. So, here are the different properties of a neutron stars, and neutron star mass can range between this 0.7 to 2.4 solar masses, radius around 10 to 15 kilometers, period from very fast to not that fast, and density of the core is extremely high and also high magnetic field. So, and this is a model diagram of a neutron star. So, this is it is rotating about this axis, and this is its radiation beam or magnetic axis. So, if I am sitting here, I will observe pulses like a lighthouse effect, and therefore it was named this pulsars. So, mostly the interesting thing is, so this mass and radius makes the density at the core very high, which is something very interesting, and we will come to know in the later what it does. So, to solve this thing, because they are so dense, said normal relativistic calculations will not apply. So, what we have to do is we have to solve the Einstein equation, and this was done again in the early 30s. Tolman, Oppenheimer and Volkoff came up with this equation. This is basically this hydrostatic equilibrium condition. This is the condition, and these two are the special relativistic terms, and this is the generalistic term which comes as a correction. So, this is a TOV equation. So, this TOV equation you see will need an information about P and rho, that means the pressure and the energy density. And if we know the relation between pressure and energy density, we can solve this equation, these two equations, to get the mass and the pressure. So, this is, we start with some certain energy densities. Correspondingly, we have to have some pressure, and as we go outward in dr, the pressure decreases, energy density decreases, however the mass increases. At this point, this is where the pressure is almost goes to 0, energy density goes to 0. It is called we define the radius of that star, and the mass where it saturates is called the mass of the neutron star. One thing that is important is we have to know how the pressure and energy density connects. Okay, that information comes from the equation of state. However, the equation of state that are viable here are extremely non-trivial, because at extreme densities we do not know the equation of state there. So, that is one of the challenges of solving this, because this part of the equation of state of the pressure versus energy density, the relation between the thermodynamic variables are missing. So, at this point the current knowledge is that we know the equation of state with a great degree at this till the nuclear 1 time nuclear saturation densities, and also at very high densities, asymptotically high densities, because of this PQCD calculations. However, in the intermediate densities we do not have any information. So, what to do about? So, there are many ways to proceed, and some people do this micro calculations of different models and all those things. However, in this talk I will just do something which is quite different, is that these are the points that we know, right, in the low density, and these are high density, and we know that the speed of sound is bound by this thermodynamic stability at 0 and causality at 1. I will randomize the speed of sound, okay, and obtain some points. These are randomized points, and then I will do a interpolation method, okay, in this way as a function of I will get speed of sound as a function of chemical potential by this interpolating method, in this method, and then once I have no speed of sound and the chemical potential, I can calculate all the other things. So, once I do that, for first random choice, I will get a single curve. I can repeat this a lot of time, maybe a million times, depending on my strength of my computer or the supercomputing facility that I have, I will get all sorts of curve. So this is one of the equation of state. So this is the one of the equation of state which satisfies all the thermodynamic and all those bounds. So corresponding to this equation of state, what I will get is a mass radius curve. Be careful that this curve, in this curve there are these are, let us say this, take us this particular curve. Each point on this curve is a neutron star with a certain mass, total mass and certain radius. So these are all different masses. So corresponding to a equation of state, we get a one-to-one correspondence of this equation of state. So this different, but we can repeat this, right? I have said that we can repeat this continuously, and for different we will get all sorts of equation of state. It is not exhaustive, we can have an exhaustive equation of state. So this is some of the typical equation of state that one can get. So however, what is the actual equation of state is still not clear, but we have astrophysical bounds which has put several constant on the equation of state, and many of the equation of state has been rejected. So because the bounds are this, it has to produce two solar masses which the pulsar has been observed with a certain radius and all those things. So we are in a better state now, but still a lot of things need to be done. However, for this case, you have seen that this is a smooth equation of state. However, we know that this is not the only choice. We can even have a first order phase transition. Okay. So first order phase transition is, that is, there is a discontinuity jump in the energy density or the number density, but the pressure of the chemical potential is continuous. So if I have the first order phase transition, I can again construct a numerous equation of state, okay, and this is how this first order phase transition, this is the transitions point of different strength, and it can originate from a different point of this is the phase transition point where it is happening. So these are different type of equation of state. If I have this type of equation of state, then my equation of state diagram is completely different. This is different from this one. This outline is the smooth equation of state, all the ensemble of smooth equation of state that we have. However, if we have a first order phase transition, you can see this ensemble changes, okay, and we have constructed this. So what is the specialty about this, or what is the thing about this? Is certain things that comes up is the twins. What are twins? You know that I am referring to twins in this case is that these three are of, you can see their volume, shape, height and all those things are different. However, their masses are same. In my definition of twins, I will just adhere to this and I will define twins in a certain way. So what I am talking about, a speciality of twins is that in some cases where we have constructed this discontinuous for different discontinuous thing, what I can get in some cases is that this mass radius curve can increase and then decrease. This decrease is the instability line, unstable points, because at this point the gravitational, if you shift the if you give a small perturbations, the gravitational effect takes over and there is a collapse. However, this part is again stable. So let us say these 2 points. These 2 points you can see in this figure and in this figure, these 2 points has same masses but different radius. So this is what I am calling a twin star. I am calling twin star this cases, same mass but different radius. Okay. So and because you can even see in this diagram that there can be different types of twin. One is if my mass radius curve can increase till here and then it can dip and then go up. These 2 stars can be twins, or it can increase till here and then go down. Then these 2 stars are twin stars. So there can be different types of twins depending on how I construct my equation of state, and that is exactly what I have done. So these are different categories of twin, and I have defined a certain category 1, 2, 3 and 4. How I have done that is that I will say that category 1 twins are twins where these 2 masses at very high mass, they have the same mass but radius is different. So these are category 1 twins. This has been categorized. This is the category 2 twin, where the first branch, this is basically the hadronic branch, it goes up till 2 solar masses, then it comes down, and here there is a stable point. These 2 stars are twin stars, these are called category 2 twin stars. We can have also this type of case which I have shown earlier. This is the first hadronic branch, this is the second, let us say, quark branch, and these 2 stars have same masses. These are called category 3 twins, and this is the one extra special category is that where the first branch doesn't go above 1 solar mass. Why is 1 solar mass? Because most of the stars, neutron stars measured till now are above 1 solar mass, barring one pulsar which is an Hess mass. So, mostly these are my 4 type of twin star that I can have, and let us now examine how these twins are different from normal stars, not only normal star, but different but stars which are formed from first order phase transition. What are the speciality about it? So, how to differentiate them, how to filter out twins by measurement or some by astrophysical measurement. So, there is a thing that goes by the name of universal relation, is that this I, love and Q, I is the moment of inertia, love is the love number, and Q is the quadrupole moment. Love number is basically a constant of proportionality. If we have a tidal field and our neutron star will have some, for this tidal field, the quadrupole moment of the neutron star can change, and this relation between this tidal field and the love number proportionality is the love number. Okay. So, this has an interesting property, is that whatever equation of state you take, because I have previously told you that the equation of state are unique, right, because given a equation of state you have the different mass radius curve. Your mass, if you change the equation of state, your mass radius curve differs. However, if I take this these 3 quantities and I make them dimensionless with a particular way, then this shows this is the black curve is the fitting parameter for all smooth equation of state, and then all this if I plot I versus love number, this lambda is the love number, then they fall in the same line. It does not matter what is the equation of state, it is independent of the equation of state, therefore, it is called a universal relation. However, for twins you can see that in twins, when it goes to the other branch, this universal relation starts to break, and it is more clear in this category, in the third category of twin, is that once there is an, so these are normal smooth equation of states, they follow a very universal relation, but suddenly if once there is it goes to the second branch where the star can have a quark core, this universal relation starts to break. Okay. However, at very high or high densities and low densities, they again follow the universal relation. So, this is one of the way of differentiating twins or first order phase transition from normal smooth equation of state. However, these are for only one equation of state. These are mass I and lambda for one equation of state. So, what about if I plot them for all sorts of equation of state that I have constructed, let us say 10,000, 50,000 equation of state. So, see this fit black curve is for a smooth equation of state. They does not show any deviations. They are very smooth, and they follow this polynomial. Okay, this fitting parameter, where these parameters are given here. However, if I plot the first order equation of state, they see that there is quite a significant variation. Okay, now the first order equation of state I have shown you is depends on what is the density discontinuity that we have considered, okay, delta epsilon, and also on the point of where the phase transition is happening. It can happen at very low densities, it can happen at very high densities, and we can see that the deviations depends on the delta epsilon. What is the density discontinuity? However, they do not depend much on the point of phase transition, because this different color shows where the phase transition is happening. There is no way of differentiating them. So, normal first order equation of state depends mostly on the deviations from the universality, depends mostly on the density discontinuity. However, for twin stars, these are different category of twins. Green is the category 1, red is the category 2, and these are the category 3 and category 4. Here I have plotted again this I versus lambda and also this fractional percentage error. This shows how much it differs from this fitting parameter, and we can see that there is this category 3 and 4 and also category 1 and 3 differs. Then how to, let us check how they depend, whether this deviation from this fitting parameter for the twins either depends on the density discontinuity or where the phase transition is happening. So I can plot the maximum deviations as a function of the point of phase transition, and I can see that for category 3 and category 4 this maximum deviation is dependent on where it is happening. So the more earlier the phase transition happening, the more is the deviation. However, there is no such trend when I am seeing the maximum deviation as a function of the density discontinuity. Therefore, for normal first order phase transition, the deviation from universal relation depends on the density discontinuity. However, for twins it depends on the where the phase transition is taking place. So this is a way of filtering out the twin equation of state, because twin equation of state has, yes, is the density discontinuity, the first order phase transition. Yeah. Okay. So this is one way of differentiating twin. Is there any other way? Okay. There can be, which is where I come into, is the binaries. What are binaries? You have already know this curve is the gravitational wave from this 1708-17, where two neutron stars merged to give off gravitational wave, which was recorded in LIGO, Hanford and Livingston, and Virgo was beyond the horizon of the Virgo, so it didn't recognize. So what happens in this binary merger is that two neutron stars merged to form a hypermassive neutron star. I will tell what is a hypermassive neutron star to give off gravitational wave, and ultimately it formed and rigged down to form a black hole. So what exactly happened is that these are the two neutron stars, they are spiraling each other. They ultimately touched each other and collapsed, and one of the way of is that they can promptly, if the mass is very high, they can promptly decay into a black hole. However, if the mass is not sufficiently high, they can form this point B, which is the hypermassive neutron star. That means this neutron star is stable for few milliseconds. However, ultimately once few milliseconds evolves, it can, because this is balanced by differential rotations, normal rotations. However, once this ceases, it again can collapse to a black hole or form a supermassive neutron star. A supermassive neutron star is stable for few seconds, 2 minutes. However, again if once the rotation stops, it can again collapse to a black hole or form a normal neutron star. So this is the black hole formation. These are the different, depending on the mass of the two neutron star collapsing, we can have all sorts of final population. However, and in the gravitational wave side, this is the inspiration, the signal from the spiral part. This is called the chirp signal. Okay, and this is the transient, is that this part, which is where all sorts of things happens, because they first touch each other, they have a lot of rotational velocities and all those things, but after it settles, after few milliseconds, 2 to 3 milliseconds, we have a constant well defined amplitude and frequency. This is called the post-merger hypermassive neutron star signal, and ultimately it collapses to a ring, it rings to form a black hole. Okay, so this is for this part of this. So these are the gravitational wave signal. Now, so this was done previously. How do I help my case of twins with this? So to do this numerical simulations of this and analyze, we have to use again the general relativity, but now we have to solve it in computers, because this cannot be solved with analytical methods. So what in computers, what do I do? Because we know how to solve differential equations. Okay, so in differential equations there are space dimension and time dimension are different. So what I can do is I can use numerical relativity, where there is a 3+1 formalism of exfoliation of 4-dimensional space time to 3-dimensional hyperspaces and 1-dimensional time. Is that they this exfoliate space time into different hypersurfaces, and these are the time direction in which they evolve. Different hypersurfaces at different times. So there is an evolution of time. So, and this is how this exfoliation is done. Okay, so this has we go from a 4-dimensional metric from GAB to a 3-dimensional spatial metric gamma AB. We have a normal vector which takes it in the different evolution of time. We have this shift vector, which is this shifting in the hypersurfaces in the spatial dimension, and we have this lapse function which takes from one hypersurface to the other hypersurface in time. Okay. So, once we do this, we have what we have done. What we do is we have a evolution equation and a constant equation. Constant equation are basically they are the conservation equation in a hypersurfaces. For each hypersurfaces, we solve this constant equation, and then this evolution equation takes over. So, these are the these are along with this evolution equation and the constant equation. We remember that we also have to solve the GRHD equation, general relativistic hadronic equations, which are given by this. So, once we can solve them simultaneously, we can have the evolution of the binary merger. Okay. So, this is one of the binary mergers that we have performed. So, here you see that two stars, first they are inspiring each other, and then once they touch each other, this is the maximum density, which after they touch each other, the maximum density rises, and ultimately you see that once the rotation slows down, they just blow up. That means they form a black hole. So, I can play it once more to now analyze the gravitational wave. So, this is the gravitational wave before the inspiral, then there is this touchdown, then this is inspiraling. It is not only rotating, but also it's like a top, right? It goes out and come up. So, this is the goes in, come out. Okay. So, this is the binary simulation that we have done. Now, we want to do this binary simulations. These are the binary simulations where the two neutron stars were same, equal mass binaries. However, if I want to probe the twin, is that remember this is the twin, right? These are the twin stars. In the equation of state, what I am probing is one star which central densities lies here and one star where the central densities lies here. So, if I merge the stars, two stars which are here, this will be their initial conditions. Okay. However, if I merge this star and this star, one will be this, another will be something else. This there it says that it has some quark content inside. So, their radius is completely different, and if I merge two stars from this part, we will have this. So, you can see that depending on from where I am doing these simulations, my gravitational wave signal will change. Okay. So, this is the gravitational wave signal from different. So, this green is the AA part, this pink is the AB part, and this violet is the BB part. So, we see that for the green AA part, it continues for a long time and then suddenly drops down. For this AB part, which is two different things mixing, it is completely different from that green part, and also this is different. And we can see this also, this imprint on the power spectral density, where you can see that different peaks are appearing at different frequencies. So, these peaks are very important for astrophysicists and gravitational wave analysis, because this peak tells us this is the post merger peak. This peak has not still been discovered till now. It will be probed with future gravitational detectors like Einstein telescope and all those things, cosmic explorer. However, you can see that even with this numerical simulation mergers, these peaks are different. And not only that, the ejected mass is also different. See, this ejected mass for this things is much larger than the ejected mass of the two different twin stars merging. And also, if I have the same twin, the ejected mass is very different. So, this is one way of differentiating twins using binaries. So, this I have showed you the twins of the category 2. Let us take another more extreme case is category 1, where so this difference in the radius is quite huge between the twins. So, if I now merge this, so I am either exploring this part and one exploring this part. Let us say I am exploring this part only taking these two stars and merging. So, this is the case. However, if I merging one star of the mergers belongs to this part and one part of the merger belongs to this star, we have a very different case. And then if I take two mergers from this, they are completely different. So, if I now do this analysis, you can see that the peaks are completely different. This peaks are completely suppressed. Okay. So, and again this dynamical ejected mass is completely different. So, this is one of the way of differentiating twins. So twins, so to conclude is that twins are a special category of stars. This is a special category if we have a first order phase transition in our equation of state. So, if we have a first order phase transition, the equation of state violates the universal relation. However, for those cases, you know that this violation depends on the density discontinuity. However, for twins, which is a special case of this first order phase transition, this violation depends not only on the density discontinuity, but at the point where this jump is happening. And another thing is, another way of differentiating the twins from normal first order phase transition neutron star or smooth neutron star is the binaries. So, their power spectral densities are completely different, also their ejected mass. So, twin stars are a way of observing or finding out new physics, if there is any, and whether twins really exist or not can be probed with this with the future gravitational wave analysis. So, this is our group. This part has been done by this and this 3 people. Okay. So, thank you, and thank you for your time.
Time for a few questions.
So, when you look at the mergers for the binaries, so what equation of state do you use? Because now the temperature will also rise, and then you cannot use this zero temperature equation.
No, these are not zero temperature equation of state. There is something called a adiabatic temperature which are inbuilt in this. So, this equation of state takes care of the temperature rise. So, this temperature of this mergers can rise up till about 80 to 100 MeVs. So, that part is taken care of. These are not zero temperature.
And also when one goes to such a high temperature, there can be also phase transitions. It is not proven, but there could be first order phase transitions.
Yeah. So this twins and all those things can prove those, because there is a line, right? That it can be a crossover, it can be a first order phase transition. I am talking about low densities, there is a first order phase transition. Because however, if the line continues till higher temperatures, there can again be a first order or a crossover. So, this twin binary mergers can prove those using different equation of state, because you know that if I take a crossover or a first order, my equation of state will change. So, this binary simulations can prove those part of the phase diagram.
And how will you detect it? For the tidal deformability will change, or?
No, for this, see, so this thing is that if I have a finite equation of the equation of state differs. From here you can see if my equation of state differs, there can be binary mergers, the masses can be very different. Not only masses, this merger depends on the temperature also. So, this gravitational wave signature and this power spectral density will also change. So, these are the things that we can look into to find out what are the changes in the equation of state that we can find.
Thanks.
Okay, so I have a question related to the slide neutron star equation of state. That slide.
At the beginning, right?
Yeah. Yeah, the previous to this. Yeah, this slide. So here in this bottom plot, this specific path of the equation state you are following by, I mean, constraining which conditions, like how you are getting this?
No, this is, here there is no constraint. Here only the randomizing of speed of sound. Now I can perform this million times. So I will fill this space, right? I can fill this space.
Yes.
Now I will put the astrophysical constant. What are the constant that I am using is, yeah. So these are the constant. This is the gravitational wave merger constant. These are the 2 parts. This is the pulsar constant that I am using, and these are the other 3 pulsar constant that I am using. So these are the constant I am using from those to make my equation of state to constant this equation of state. So it was previously it was filled whole here, right? Okay. So now I have with this constant I have constant my equation of state to this boundary line.
So like based on those constants like gravitational wave or Nyser, those things, so that could follow any other equation of state path?
No, all so once I have constant, then the only thing that remains is this part.
Okay.
Other thing has been rejected because they either doesn't follow any one of the constant that was given there.
Okay. And your like core category of the twin star, some of the parts you are saying not stable.
Yeah.
So like based on what? dm by d rho c less than 0 or what?
Yeah, if you plot the mass as a central densities, if you perturb the star, what happens is if you perturb it, what happens that the gravitational wave, now you change this gravitational pressure. What happens is now this perturbation, if you give a perturbation, this gravitational effect takes over and it collapses. The star is not stable one. It oscillates and then completely collapses to a black hole.
No, so I just wanted to check like radial stability, that thing has been studied, like stable against radial stability.
Yes, yes.
Okay.
That has been done.
Oh, thank you very much.
Thanks for the nice talk. I have a question which is probably not relevant, but let me still ask. So can we probe these phase transitions using continuous gravitational waves? I know that depends on the ellipticity. That's the major thing. But is there any effect here?
It can be probed by continuous gravitational wave. However, but that continuous gravitational wave probe has to be of a long time. It's not like only binary images we can do this, examine these binary images for a short time. But for continuous gravitational wave, you can probe the equation of state, but for that we need a long-term observation of that pulsars and all the gravitational waves that we are doing. It has to be a long-term effect. Here, binary images is a short. Even with a short gravitational wave observation, we can differentiate them. But for the continuous wave, it has to be very long.
Pass.
So there are no more questions.
Sorry.
When the collapse takes place, what decides at what radius it will go and settle? There are two radiuses which are available for you. Where do you find that information in the dust, if you want?
Means
where does it take place?
Radius means this twins. Sorry.
You have same mass but different radius.
Exactly. However, as you have seen, if you are careful enough, let me go back in this binaries. Sorry, I'm taking a bit of time. So here, see, if the central density is here, so the most stable thing is this one. If the central density is or the pressure or the central density is here, this stable thing is this. So depending on where your central density is, the stability of which star will depend on that. Okay.
Are there real examples in the collapse?
Yeah. Because this simulations has been studied with gravitational wave 1708-17, right? These are very exact calculations.
Well, these are all only simulations, but
the observation. So
the observations.
So for given the masses which were observed for GW 1708-17, this simulation will give you exactly the same results. Okay. There are also not only gravitational wave analysis. There are also this multi-messenger observation was done for only GW 1708-17, but there are observations where only we have detected gravitational wave, and there are observations where we have only detecting electromagnetic radiation like GRBs. Okay, so even with these simulations, we can predict those kilonova curves and all those things. Okay, so there are observations that we can predict it and check these simulations.